Good morning, guys. Today we're going to look at graphing points and planes in three-dimensional space. We've been doing this for many, many years on a two-dimensional plane. We call it the coordinate plane. So we know we have our positive x-axis, we have our positive y-axis, and then we have the negative x's and the negative y's. I've been doing this since Algebra 1, pre-algebra. For two-dimensional length and width, today we're going to work on putting some height in there, giving it that third dimension. Okay, here we go, guys. So again, we have our coordinate plane here. We have the y-axis running vertically, x-axis is running horizontally. Imagine you're sitting in a chair right here in quadrant 1 looking back at the origin. You can see how below you from this view is the x-axis, and over here in front of you is going to be the y-axis, that's to the left of you. So below we have the x-axis, to the left of you is the y-axis. When we go three-dimensionally, we still want to focus on this quadrant 1 perspective. So when we turn this around, we're still sitting over here in quadrant 1, but now instead of the x-axis being below you, it's to your left, and the y-axis is to your right, and the z-axis is in front of you. So as you can see, we have our positive x's over here to our left, negative x's are all the way over here. The y values, the positive y's are right here to our right, and the negative y's are over here on the other side of the x-axis. Positive z's are right here, and below us is all of the negative z's. So instead of working with a coordinate plane, we're now working with a coordinate space. So guys, here's the coordinate space that we're going to be using. As you can see, it's still x-axis on the left, y-axis on the right, z-axis is in front of us, just like we're sitting in that chair in quadrant 1. And we have our negative x's are back here, signified by a dotted line. Negative y's are over here to our left, and then the below dotted line, that's going to be your negative z. So this is the picture that we'll use to convey three-dimensional drawings on our two-dimensional paper. So we've just looked at how we move from two-dimensional space into our two-dimensional plane into a three-dimensional space, and we're going to dot these lines here to help us out seeing the negatives, because it's like remember, there's these walls here, got the walls there along the XZ axis and YZ, or XZ plane and YZ plane, so we can't see into those other surfaces, those other areas. So as we remember, ordered pair, that's what we call it. We call it ordered pair, because it has a specific order, and there's two numbers there. We do X coordinates first, Y coordinates second. So say I had the ordered pair 3, 3, or 3, 2. 1, 2, 3, and then 1, 2, we'll make it 3, 4, just so it matches my drawing a little bit better there. So this would be the ordered pair, over 3, up 4. And that's pretty straightforward. We went over 3 units, we went up 4 units, puts us right there at that ordered pair 3, 4. Now over here in three-dimensional space, because we're two-dimensionally graphing, or we're on a two-dimensional surface, and we're trying to do a three-dimensional point, it's a lot more difficult to see. We don't use ordered pairs. We now have a third value, so we call it an ordered triple. Ordered triple, specific order, 3 values, X, then Y, then Z. So it's just like we went before. We did our horizontal, we did our vertical, then we did our, sorry, we do our length, we do our width, and we do our height. Now, since this is more difficult to see, we really do have to do these directional arrows to tell me where I'm going. So if we're doing, say, 3, 4 again, so say I want to graph the point 3, 4, and give it a height of 2, we need to move 3 units along the x-axis. So that's 1, 2, 3 units along the x, 4 units along the y-axis. So I'm not going to go here and count 4 units because we've kind of sloped it. We've got to give it some perspective there. So that parallel 4th line would actually come out here. So while we are 1, 2, 3, 4 units on the y, we're going this distance of 4 units from the x-axis. So that's going to put us right out here. And we'll make that 3, 4, 1, just so it's a little consistent. So I'm not going 4 units back from the origin. It's figure out what your 4 units is, how long that is, and then go from the x-axis. So I went 3 units on the x, I went 4 units from the x, and now I'm going to go up 1 unit, and that'll put me right there. So we can see this trail. 3 units along the x, 4 units along the y, 1 unit along the z. Looks like it's sitting down below, but if you'll use that trail there, you can see it's actually sitting in our, right in front of us where we're sitting in our chair right here. We're in quadrant 1 and we've gone up a level. We would call that octant 1. Just so we know, remember, we're 1, 2, 3, and 4 for our quadrants. Well, the octants, we just flip over to the negative z's, and it's 5, 6, 7, and 8. So octant 1 is above octant 5, 2 is above 6, 3 is above 7, 4 is above 8. So this would be a point in octant 1 because it's got a positive x, positive y, and a positive z value. So that's how we would graph specific points in 3-dimensional space. Now we're going to look at how we can graph a line, but we don't really have lines in 3-dimensional space. In 2-dimensional space, we set x plus by equals c. That gives us a line because we have a value for the x, the y, which is both coordinates in 2-dimensional space. In 3-dimensional space, if we give a value to each, if we give a value to each component, ax plus by plus cz equals d. Now we have a plane because we've taken that line and we've given it some sort of height. So when we don't sketch lines, we sketch planes. A line actually comes from the intersection of 2 planes. That's something we'll get into in the next unit or next section a little bit. So if we're sketching a plane, it's going to be very similar to the strategy you first learned when you were sketching a line in 2 dimensions. And that was using your intercepts. If I can find my intercepts, I connect the dots. Now it's very difficult to graph a plane in 2-dimensional or on a 2-dimensional surface because a plane keeps going in every direction. So what we use the intercepts for is to give us an idea of how the plane intersects and passes through this area that we're sitting in, this area that we're looking through. So if I'm going to sketch this, I'm just going to find the intercepts. So to find the x-intercept, I'm going to take my y's because x-intercept is where I am on the x-axis. I have no y value, no z value on the x-axis. So I just take 2x plus 3 times no y's, 4 times no z's, set it equal to 12. When we do the arithmetic there, you get 2x equals plus 0, so just 12. And when we solve, we get x equals what? 6. X equals 6. So our x-intercept is 6. So I'm going to come over here and plot 6. 1, 2, 3, 4, 5, 6. All right, now let's do the y-intercept. Y-intercept has a y value, but no x's and no z's. So 2 times no x's, 3 times whatever that y-intercept happens to be, 4 times 0 z's. Go through, 0 and 0 cancel. So 3y equals 12, and we know that y equals what? 4. So I'm going to go to 4 on the y-axis. 1, 2, 3, 4. So there's 4 on my y-axis. And then finally, let's do the z-intercept. So we have no x's on the z-axis, no y's on the z-axis, and z happens to be whatever the intercept is. So we simplify that. For z equals 12. Solve, we get z equals 3. And then we're going to go to 3 on the z-axis. I'm going to start by connecting the x-intercept and z-intercept. We call these traces. The line that passes between two axes is called a trace. So, between the x-axis and z-axis, we get the xz trace. Between the z-axis and the y-axis, we get the yz trace. And between the x and y axes, we get the xy trace. Now what that does is gives us a snapshot of the plane, of this plane as it's passing close to the origin. So we see that we get this plane right here, and it's coming through at an angle. It's coming from the z, positive z, and it's going to pass through. So if we're sitting here in our chair in quadrant 1, you can think, okay, maybe 3 feet up on the wall, a plane starts to pass through, and it's going to hit about 6 feet out on our left wall. It's going to hit 4 feet out on our right wall, and we see this plane come through. So it's going to look like a triangle to us because it's hitting all three surfaces in that quadrant 1 in that chair we're sitting in. And that just gives us, like I said, a snapshot of what's going on right there at near the origin, right where we're sitting in our chair in quadrant 1 looking back towards the x-axis. Now I do want you to identify what these traces are, the actual equations of the trace. So for the xy trace, it's just an equation of a line. We've got 2 points there. So we had our x-intercept, which was 6, 0. Y-intercept, which was 0, 4. xy. And you just go through your equations, or your steps for solving an equation. So, slope equals y minus y, 4 minus 0, over x minus x, 0 minus 6. So 4 over negative 6 is negative 2/3. Put that into slope-intercept form. Y minus y1, and it doesn't matter which y you use, I'm going to use that one because it's a 0, equals the slope times x minus the x coordinate. So y equals negative 2/3 x. 2/3 times 6 is good. A negative makes it positive, 4. And then we go through and we just get everything back on the same side together. So we get 2/3 x plus y equals 4. Let's distribute that 3 to get rid of that denominator. So 2x plus 3y equals 12. There's your xy, or your xy trace. Now let's do the YZ trace. Now the YZ trace is going to use the Y-intercept and Z-intercept. So the Y-intercept, we already said was, well, we've kind of got to redefine what our ordered pair is going to be. So if we go with a Y comma Z ordered pair, as long as we're consistent, it'll always work out. So our Y coordinate is 4, Z coordinate is 0, And then if we'll go right here, we were 3, so 0 y's and 3 z's. Going through the process. So slope is y2 minus y1, or sorry, z2 minus z1 in this case. Z2 minus z1 over x2, or y2 minus y1, 0, 4. 3 over negative 4 gives me negative 3/4. So again, consistency. So instead of it being y minus y1 equals m times x minus x1 for our slope intercept, we're letting z be that second coordinate. So it's z minus z1 equals the slope of y minus the first y coordinate. So we do z equals 0. Sorry. Z minus 0 is z. Multiply here, negative 3/4 y. Negative 4 and negative 4 should cancel and give us plus 3. Move our negative 3/4 over. Equals 3, and again we're going to multiply by 4. So we get 4 times 3 is 12 over 4, which gives us 3. So 4's cancel. 3y plus 4z equals 12. So that's going to be our yz trace. And then we'll finish with the xz trace. X-intercept we already said was 6, 0. In this one, I'm going to use an x comma z ordered pair. I could do z comma x, and as long as I'm consistent with first variable is going to represent, has to represent like your x's and in your normal slope and slope intercept and point slope formulas. Second coordinate has got to represent your y's in those same formulas. But I'm going to use xz format. So 6 comma 0. The z is going to be 0 comma 3. Go through the same process again. Let's do our slope. M is equal to 0. Order doesn't matter, so we'll do 0 minus 3. 0 minus 3 over 6 minus 0. So as long as I'm doing the same one first. So if I did 3 minus 0 over 0 minus 6, I would get the same thing as I'm doing from 0 minus 3 and 6 minus 0. Negative 3 over 6 is negative 1/2. Then not y1, and it's not y minus y1, it's z minus z1. Because z is our second coordinate. Equals the slope times x minus x1. Do the arithmetic. Z minus 0 is z. Negative 1/2 when we distribute it gives us negative 1/2 x, negative 1/2, and negative 6 is positive 3. Add my 1/2 x over. Plus z equals 3. Let's get rid of that half. So 2 times 1/2 is 1, because 2 and 2 can cancel. So 1x plus 2z equals 2 times 3, which is 6. And that's going to be our xz trace. Let's go back and look at the original equation for the plane one more time. 2x plus 3y plus 4z equals 12. And let's look at the traces again. XY trace was what? 2x plus 3y equals 12. 2x plus 3y, it's just the xy, so there is no z to it, equals 12. YZ trace, 3y plus 4z equals 12. 3y plus 4z equals 12. There is no x in the YZ trace. And the XZ trace, XZ, 2x plus 4z equals 12. Well, we didn't get that. We got x plus 2z equals 6. So why are they equivalent? Y is this, and this, the same thing. It's because it's a scalar. We're talking about a line that goes on forever. Well, if I've got a line that goes out for infinity, x plus 2z equals 6 goes out for infinity. If I make that line twice as long and get 2x plus 4z equals 12, what we see right here, that's just a line twice as long as this line. Well, if it's going to infinity, that's the same line. So if you take a line and multiply it by a scalar, just making it bigger or smaller, it's still a line. It's still going forever in both directions. So those are equivalent, and that will give you a quicker way to get your traces. X, y, put your x and y together and reduce it. If they can all divide by the same thing, we divide by the same thing. Y, z, put your y and z together with the constant and reduce it. They can all divide by the same thing, divide it. And same thing for your x, z. In this case, see how they all could divide by 2, so we just reduced everything by 2. Now that's how we graph points in three-dimensional space and planes in three-dimensional space. We'll use this to transition into solving systems in three-dimension or with 3 variables, because just like solving systems in 2 variables where lines intersect, solving systems in 3 variables is where the planes intersect. And I will see you in class tomorrow, guys.